This conference will now be recorded.
Okay, I think in the last class we have discussed about basics of HDL, why it is required and all, right? Say you are designing one AND gate IC, right? You're designing one AND gate IC. So for that, first you need to do is you need to write a code, hardware description language. Like either you can write in VHDL or in Verilog code, right? So that code you need to write. Then that code should be uh, checked with the help of simulator, that is Xilinx. Then once it is working fine means, then you can do the synthesis part. Means the same code you can convert it into schematic, right? Then followed by fabrication. Then finally your IC will be ready, right? So that is the procedure. Fine, correct, right? Right? Okay.
Yes, sir. Yes.
Any doubts here till now? Any doubts? So before
No, sir.
fabrication and all, we are using your HDL code, right? So once it is working means that same code you can dump onto the kit, right? That is FPGA kit. That is field programmable gate array. That field indicates that you can use this FPGA kit anywhere. Okay. For that you require one supply and all. That's it. Fine. Then gate array means your FPGA kit. That is in our lab we are using Spartan kit. It has got n number of gates. Getting my point? It has got n number of gates. So say you have dumped one AND gate. That code. We have dumped one AND gate code onto your Spartan kit. Then what happens is out of n number of gates, only that particular AND gate, that is two input AND gate, will be enabled. Okay, that part we will be discussing in the lab in detail. Okay, so today what we'll do is we'll check some of the Verilog programs. So how to write and how exactly you can run. Is that fine? Is that fine? And one more
Yes,
thing I
sir.
would like to, sorry, any doubts?
No, sir.
Okay, fine. So now what we'll do is, and one thing I would like to clear that your HDL has two languages, VHDL and Verilog. VHDL contains two parts. There is entity and architecture, whereas Verilog has the single part, that is module part. Within that module part, you are assigning all the ports followed by description. Means you're just showing all the connectivity between your inputs and output. So it has got a single part in case of your Verilog HDL. Okay. So I'll just share some programs here. Hope you can see this. And before that, I'd like to brief the syllabus. Can you see this? Yeah,
Yes,
first
sir.
Yes,
model
sir.
is overview of digital design with Verilog HDL. So how it has started and all, right? Then hierarchical modeling concepts, as I explained in the last class, top-down approach and bottom-up approach. Differences between modules and module instances, parts of simulation, design blocks, and all, right? So that part is covered in module 1. Then in module 2, we are learning about lexical conventions, data types, system tasks, compiler directives, followed by modules and ports. Module definition, port declaration, connecting ports, hierarchical name difference. Okay. Then module 3, we have got two parts again, gate level modeling and data flow modeling. Then module 4 will discuss about behavioral description or behavioral modeling, where we can learn structured procedures, initial and always. Okay. tasks, functions, differences between tasks and functions, declaration, and all. So these things we'll be discussing in module 4, whereas in the last module, modeling techniques followed by logic synthesis with Verilog. Right? So, okay. So now, yeah, this is the lab part. It it initial 58. Okay. So you can today what we'll do is we'll check some simple Verilog programs. So is it visible? Can you see the full screen?
Yes, sir.
Fine, right? Okay.
Yes.
Okay. So say first one, write a HDL code to realize all the logic gates. So can you tell me what do you mean by a logic gate? So logic gate or any logic can be anything, AND gate, OR gate, XOR gate, NOT gate. It's an electronic circuit which can take some decision, right? Say you are checking two input AND gate. Means what it will do is, in case of two input AND gate, it will take two inputs and will produce a single output. And how what exactly it decides? So whatever the inputs it is receiving, it will multiply both the inputs, and whatever the uh, whatever the value you are getting, that will be stored at output. Right? So that decision is taken by your AND gate. Similarly, OR gate means it is logical addition. So whatever the inputs you are providing, that is being added by your two input OR gate, and output will be stored at some particular variable. Fine. Okay, so AND gate, NAND gate, NOR gate, AND gate, OR gate, NOT gate, XOR gate. So here, can you see this? It's a Verilog code to realize all the logic gates. So what we are doing is always Verilog code. It will start with one predefined word called module, followed by all gate. So what is this all gate? All gate is the module name that is being given to our code. You can give any name, even you can give your own name. Okay, and what you are passing inside the brackets here: A, B, Y, and Y or Y not, Y NAND, Y NOR, Y XOR, and Y XNOR. So here, so whatever the gates we are showing over here, they are all two input gates. And NOT gate. Can you see the NOT gate area? Here it is. NOT gate is the only gate that takes only a single input. So here. Then inputs are A and B. Outputs are 1, 2, 3, 4, 5, 6, 7. So how many gates we are checking over here? 7 gates we are checking. Okay. See, if you want, you can write a single code for each gate, or else you can show, or you can realize all the gates within a single Verilog code. Same thing I am doing over here. So first I am checking AND gate. So assign Y AND equal to A and B, followed by semicolon. Semicolon will indicate end of your sentence. Okay. Similarly, for OR operation, assign Y or equal to A or B. Similarly, for NOT gate, see, it's not mandatory that you have to use Y and at the output set. You can use any name. Why have you taken all these Y and Y or? Because it will be easier for you to do. Okay. So while checking, it will be convenient. Okay. So AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate, and XOR gate. And one more thing you can notice is between the inputs I have shown symbols instead of words. Right? Suppose say you are writing HDL code, means you are writing one VHDL code. So there you are not supposed to use assign, and instead of symbols you need to use the words. Right? And again there you need to use entity as well as architecture. Fine. So next is write a HDL code for the following combinational circuit. So combinational circuit means what it is? The output is dependent only on the input. If that is the case, then you can call it as a combinational circuit. Correct? You can take any gate, then your encoder, decoder, multiplexer, demultiplexer, right? These you can call as combinational circuit because output is dependent only on the inputs. Then what do you mean by sequential circuit? Sequential circuit means again it's a circuit, right, where your output is dependent on two things. One is input, one more thing is previous output, right? So 2 to 4 decoder, it's a combinational circuit because output is dependent only on the inputs. So this is a schematic for 2 to 4 decoder, right? So it can take two inputs. One is the enable input, it's a mandatory. Then Dean is the input. What is this 1:0? It will show that your Dean can take 2 bits at a time, starting from 0001 1011, right? And enable, either it's a single bit, can be made as either 0 or 1. Okay. So next D out 3 to 0, 3 is to 0 means again it can have how many values? 0000 till 1111. How much it will be? 2 raised to 4 means I can expect 16 combinations here. Getting right? Any doubts here? Abhinandan, any doubts?
No, sir.
No, right. Okay, now you can check the truth table here. So in this truth table, you can find enable, DIN 1, DIN not. So this acts as LSB, DIN 0, DIN 1 acts as MSB. So since it's a 2 to 4 decoder, these two are inputs, fine. So these 4 are outputs. I can call it as a active low enable. Active low enable means it will start giving you the proper outputs if your enable is made as low. So here, if enable is 1 or high, it will not check the inputs. XX means don't care. It will not check inputs. Irrespective of the inputs, it will produce all the outputs as 0000. Right? Okay. Next, since it is active low enable, so check the second row. If enable is 0, then if you are giving inputs as 00, it will be giving you the output as 0001. Means D naught will be high, other 4 they will remain 0. Right? Then for again for enable as 0, then for 01 input, it will make D1 as high. Then for 10, D2 as high. Then for 11, D3 as high. At the same time, other bits will remain 0. Getting? So how about code here? Verilog code. Verilog code. What's here? Module, decoder 2 to 4. And how many inputs and output it is considering? Enable. You have to give enable, right? Then DIN is the input and DOut is the output, right? Then inputs are DIN, right? DIN can hold 2 bits at a time, like 0001 1011. Then output DOut, it can hold 3 bits at a 4 bits at a time, starting from 00002 to 1111, right? And one more the keyword we are using in Verilog code is especially if you are specifying any range in the code, means you are using one predefined word called register. So this will be discussing later why you need to use and all. So this register we are using mainly in the Verilog code. And here always @ enable comma DIN. Before explaining this, I would like to tell one more thing is mainly we have two types of descriptions. One is data flow description, one more is behavioral description. So data flow description means uh, if you are just showing the relationship between inputs and outputs, right? Then you can call it as a data flow description. Then behavioral description means you are writing the code with respect to the truth table. Getting right? This is important concept. In case of data flow description, right? You are just after the model or after the code declaration and all, you are just uh, showing the relationship between inputs and output. But in case of behavioral description, what we are doing is we are writing the code with respect to the truth table. So I can call it as a behavioral description. In behavioral description, we are using one keyword called always @enable, DIN. You have to use enable. You have to use always, right? Followed by enable and DIN means you are just passing all the inputs here. Enable and DIN, right? Then begin. Again, it's a predefined word. So see, as I explained, it's a behavioral description. If you check the code here, the code I have written with respect to the truth table. Okay. Now, so once I finish this, then you can compare both. So if enable is 1, what it has to do with respect to your truth table? If enable is high, irrespective of the inputs, it has to produce all the outputs as 0. Right. So I've used if enable is equal to 1, right, then d out 4 dash b 0000 means, see, 4 dash means your d out can hold 4 bits at a time. B0000 means whatever the b you are checking here, it's a binary type, so all 4 outputs will remain 0. When you can expect all 0? If your enable is made as high, then I'm just closing this if, then else again begin. See, now I am using one case. Why I have taken case? Because if enable is 0 means, then I am left with 4 iterations or 4 cases. 2 dash b00, if inputs, that is d in, is 00, what about d out? It is 4 dash b0001, means this b naught will be of 0 will become 1. If it is 2 dash b01, if inputs are 01, then d1 will remain high, other bits will remain 0. For 10, uh, 10, it is d2 will remain high. Then for 11, last bit, that is d3. Then end case. So here I am closing the code here. End case, yeah, case, I'm just closing the case here, then end. Why I have taken two ends? Because I need to close both begin here, right? So to end, then finally I am closing the model, end model. Now we can check here. If enable is 1, all outputs are 0. Check the table. If enable is 1, irrespective of the inputs, all the outputs d0, d1, d2, d3, they will remain 0. Else means you can take these 4. Else for 00, d0 will remain high. For 0, like this, you can check. For all these 4 cases, your enable will remain 0. Then for 00, d0 will remain high. Then for 01, d1. For 10 or d2. Then for 11, d3. So any doubts here? Any doubts till here? Any doubts?
No, sir.
No, right? Can you do one thing? I think you have pen and paper. You have pen and paper, right?
Yes, sir.
Yeah. Can you write one Verilog code for 3 to 8 decoder? Can you write one Verilog code, right, for 3 to 8 decoder? Is it possible?
So I will try.
Yeah, you can do that. Thing is, you can start with RTL schematic followed by, see, in RTL schematic for 3 to 8 decoder. 3 to 8 decoder means 3 inputs, 8 outputs, and 1 enable. So in that 3 to 8 decoder, what about the in range? I can say 0 to 2. Correct? Yes or no? Hope you are getting me.
Yes, sir.
Yeah.
Yes.
So for 3 to 8 decoder, the range for DIN will become 0 to 2, 0, 1, 2. So 3 inputs, 1 bit enable. Then what about D out range? It will become 0 to 7. Correct? 0 to 7. Then truth table, how it looks, enable. So inputs D in 0, D in 1, D in 2. Then outputs D out 0, D out 1 till D out 7. Can you try that right now? I'll give you 5 minutes. Will you try now or afterwards? I think you have sufficient data. Okay, you just take it as exercise. Okay, afterwards you can try. Fine.
Okay, sir.
Yeah, afterwards you try because it will take some time. Instead of wasting your data, I'll start with one program. Okay, that will check in our Xilinx simulator. Okay, that will check in our Xilinx simulator. Is that fine? Okay, just check here.
Yes.
So this is our simulator. That is Xilinx 9.2 version. So in this simulator, what we are doing is whatever the code we are writing, right? That we are checking with respect to some text range waveforms that we'll see now. Yeah, after opening this, so this is our simulator, that is Xilinx 9.2. Click on File, New Project. In lab, we'll be checking this in detail. So project name, you can give any name. So we can check any program. So let us take and gate. Okay. So path, if you want, you can change here. Project location and gate. Okay. Now, sir, here you can find some different options. Family. So yeah, automotive 9500 Excel. Synthesis tool, again XST, VHDL or Verilog. So sir, uh, preferred language, it will ask. Preferred language, if you are writing the code in Verilog, means you can keep it as same. Otherwise, you can make it as VHDL. Fine. Since we are writing in Verilog, I am changing it as, I am changing preferred language as Verilog. Fine. Then click on next button. Source file, new source, again Verilog module. I can give any name and get 1, 2, 3. Click on next. Now see here, this is the port declaration. This is port declaration. As I am checking two input and gate, I need to have two inputs and one output. So see here, you can take any variables A, B. So see here, AB direction is input. If it is output means you can change it as output. So A and B as inputs. See here. Suppose say you are writing for 2 to 4 decoder, means input can hold 2 bits at a time. Then you need to use bus followed by that range 0 to for 2 to 4 decoder. For D in you can make it as 0 to 1. Then at the output side 0 to 3. Then you need to make it as output, that we'll see later. So first we'll check this. So as it is two input and gate, A is the input, B is the input, and both will take only 1 bit at a time, either 0 or 1. Then what about C? C is the output here. Only this part is enough for us. A input, B input, C output, and all these three variables will take only 1 bit at a time. Click on next. Now you can cross verify. A is the pin input, B is the pin input, C is the pin output. Finish. It will ask the directory C Xilinx 9.2i and get does not exist. Would you like to create? Say yes. Right. Next. Next. So what you did here? So I have created one. So I have written one code in Verilog and also assigned some ports here. So once you assign all the ports and all, see now you can see one dialog box here, two windows, and in the first window you can you see this V? V means it will say double click on this, so it's a Verilog code, right? So automatically it will show all these things. Module name we have given AND gate 1 2 3 A B C. Input is A, input is B, output is C. Next, we need to write one line, that is assign C equal to A and B. Am I correct? Within the module, I need to assign all the ports. It has already been assigned because we have already shown all the inputs and outputs. Only thing we need to write is we need to write means we need to show the connectivity between inputs and output. C equal to assign C equal to A and B means just we are showing the logical multiplication, right? Then so this part is over, right? This is a code to realize one two input and gate. Fine. So save this code. Then you need to check for any errors. So for that you click on implement design, right? Synthesis, it's a ST. Then here you can find check syntax. Click on this check syntax. Click on this check syntax. So here it is showing it's fine. It does not contain any errors and all. Okay. Once it is over, once your code is fine, then you can go for test bench waveform. For that, you need to click on this part, create new source. Again, you can select Verilog module. See, whatever the name you are showing over here, it is related to your test bench waveform. You can give any name, say 999. So 999 is the test bench waveform. Okay. Wait. Something went wrong. Create new source. Sorry. You need to click on test bench waveform because now we are into simulator part. So test bench waveform, give any name, say 999. Okay. Getting so test bench waveform followed by name, Next, close this. Click on combinational clock, finish. Now sir, you can find three waveforms here: A, B, C, or three lines. A, B, you can change. Means you can have control only on the inputs. 0, 0. See, say this is the first iteration. Iteration 0, 0. This is 0, 1. This is 1, 0. This is 1, 1. Is it looking like your truth table? A 0, 0, right? Then, sorry, if you are checking with respect to A and B, it is 0, 0, 0, 1, 1, 0, and 1, 1. Correct? So next, save this test bench waveform. Right? Then click on behavioral simulation. Processes. Click on this simulate behavioral model. So it will display, it will check once again. So if you are checking with respect to simulator means, click on create new source, test bench waveform, say and get, right? So and 333, you can give any name. Zero 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 one one zero one one. Save this. See here, you can check this and 333.tbw means test bench waveform. Whatever the simulation you can see next, that is related to your inputs. Okay. Now click on processes, Xylem simulator. Click on this simulate behavioral model. Means it will simulate one behavioral model with respect to the given inputs. So click on this. Okay. Now you can zoom out. Save. If inputs are 0, 0. So sir, if inputs are, see, this is output, C is the output, A and B are input. So this is the simulation that we have generated. Okay. So if inputs are 0, 0, output is again 0. Then inputs are 0 and 1. You can check here. Inputs A is 0, B is 1. What about C? It is still 0. Next. Next iteration, A is 1, B is 0. If A is 1, B is 0, still your C is 0, means low. Check the last iteration. If both are high, then it will become high. Is that fine? This is the way we used to simulate any code. So any doubts here? Any doubts?
No, sir. No, sir.
Till now clear? Any doubts? It's clear, right? So we'll check one more program. Is that okay? So this is for 2 input AND gate. So clear? Check clear the simulator part. The output will remain high if both the inputs are high. So here means you are getting output as high only if both the inputs are high, 1, 1. For other three cases, it will remain 0. Okay, we'll check one more program. So take new project. So which one? So we'll check NOT gate, right? So for NOT gate, we require only a single input. So NOT gate, Verilog code, new source, not 111. You can give any name. One input, one output. Right? A is the input, B is the output, and both will take one bit at a time. Finish. Okay, now sir. This is for NOT gate. Model name NOT 111, and we are passing both inputs and output. A input, B output. What I can write? Assign C equal to negation of A. Checking the symbol here. Negation of A. Copy from this file. Is it C or B? It has to be B, right? Negation of A. Is it correct? So B equal to negation of A means whatever the input you are giving, that will be complemented by your output. Fine. So it's about NOT gate. Then save this. Check for any errors. Yeah, it's working fine. So once code is running properly means, then you can go for test bench waveform to generate the simulation model. So click on this create new source, test bench waveform, give any name, say not 5. Okay, click on combinational clock, save. I can find only two things. One is input A, one more is output B. So this is 0, 0, 1, sorry, 0, 1, 0, 1. Correct? A 0, 1, 0, 1. So save this. So with respect to this test bench waveform, we need to generate the simulation. For that, you click on behavioral simulation. You can find the test bench waveform, not5.tbw. Okay. Then click on processes. You can find one Xilinx IC simulator. You enter into this. Click on simulate behavioral model. Okay. Now zoom out. So save. What you can conclude from this? First, you can find the output. Next, input. If input is 0, output is 1. If input is 1, output is 0. Means they'll complement each other. So A is 0, B is 1. A is 1 means B is 0. So is that fine? In the lab, we are using the same thing. Means same simulator we are using. So first we are checking the output with respect to your simulator for 3 to 4 programs. So once you are perfect, then you can check the same code with respect to your Spartan kit, or that is FPGA kit. Up to this clear? So any doubts here? So any doubts? Nivedita, any doubts?
No, sir, it's clear.
Yeah, clear, right? Okay. Yeah. So next class, we'll start with module 1. Okay. Gate level modeling and all. Yeah. Thank you. And before, try to write that, try to complete that assignment that I have given today. So what you need to write? You need to write a Verilog code to realize 3 to 8 decoder. Is that fine? Yeah, you just try at home.
Yes, sir.
Yeah,
Okay.
yeah. Thank you. Thank you for
Thank
joining.
you, sir.
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you.